Hello, hello, hello there. We're at issue number 5, exploring our package with Chipmunk. The topic is more learnings. Cats and stats, let's get started. So today's packages will include a set on tutorials, dhur and Kern Lab, as well as some classic stats, Asymp Test, Hardy-Weinberg, IRR, and vacuum. Now a couple things that we are crossing out here is Pogromcy Daniec, I think it's Polish, and then Zelig. I had those slated, but turns out this first one here, rather than being a tutorial, is mostly just data sets, and then Zelig is no longer available. It was removed from the CRAN repository. With that paperwork out of the way, let's get started. So here are our summaries. dhur is built as a fast interactive tool built on the learner function. It's paired with these Learning R with Dr. workshops. So we'll dig into that. Kern Lab is kernel-based machine learning methods. So not so much of a tutorial, even the lab's in the name, but just typical methods for machine learning. Asymp Test is 1 and 2 sample mean and variance test, and this, there's a little more to it than that, but we'll take a look. Then Hardy-Weinberg, if you know anything about ecology, genetics, these are for tools for exploring the Hardy-Weinberg equation, especially equilibrium. Then IRR, it's iterator reliability, so there's various coefficients to calculate in this package, and then also for various agreement coefficients. And finally, vacuum, this is the implementation of these 3 procedures by John Tukey, so very classic. They have them labeled in acronyms FRANOP, FANOR, FANOM, and vacuum cleaner. So we'll get to all that in just a moment. So let's glance at them and see what they have to offer us. First on the docket, dhur, Learning R with dhur. So these have a reference and a vignette. Let's look at the vignette first and then the PDF later. So the vignette looks like there's a set of 4 tutorials here. Plain, so basic data structure, input and output. Munging, which sort of means modifying, I guess in coding speak, and then analyzing and visualization. Okay, so that's about here. And with some of the wording here, I think dhur is from China, so this is not English is second language, so some of the wording is like, for example, things like a little bit easier and more happily. So some transitions is a little off, but overall I think it's not too bad. So if we look at the package here in more detail, there's really just one function dhur, and you call it, and then you call it for the different versions, so plain, munging, analyzing, and visualizing. So that's what we got there. Okay, moving on to Kern Lab, so this kernel-based machine learning. You do things like classification, regression, clustering, novelty detection, etc. So got a nice vignette here, as well as a PDF. So looking at the vignette first, this is more like structured like a paper, got an abstract, introduction. So a lot of good resources here, reviews software, talks about the Kern Lab, objects, and I kind of go down here. So it's dealing with a lot of these kernels, which I'm not too familiar with the kernels, but essentially they're an inner product of 2 vectors, and that's important for various things in math and machine learning. Again, machine learning is a bit of a black box, but this is hopefully a helpful resource if those things make more sense to you. And it looks like one of the main functions is going to be Kernel Matrix, the most commonly used function for doing these. Computing the matrix K, where it's a row vector. Anyways, we'll kind of scroll down here, more methods, using a support vector machine, etc. And also this KSVM that's generating the support vector machine, looks like that's used a lot, so we'll do some examples. Here's some nice graphs they have of decision values for like classification, so that's kind of cool. We'll replicate that. Some other stuff here for, I think, Gaussian processes. It's kind of cool spiral stuff, I guess, to classify 2 different spirals, etc. So, a lot going on here. Then just go into PDF, or not the PDF, just the PDF. Documentation, there's a lot going on. There's a lot of internal functions like class, but then other just regular functions, so seems like to be a lot going on here. Okay, with that, we'll keep moving and grooving. We have Asymp Test, so it's classical parametric statistical tests in constant intervals and large samples. So they're sort of set up like 1 and 2 sample mean and variance tests. So they're set up in the same way as the student's t-test, so you can sort of compare this to a classical t-test. It also says it fills a gap of a non-normality alternative to a chi-square single variance test. So package might be useful for that application that you can't get anywhere else, apparently. Anyways, let's just dig into this a little bit. There's only 3 functions here. The main one, Asymp Test, I think a data set, and then set error, the mean calculations. So pretty small, just really for if you need these tests. Okay, next we have Hardy-Weinberg. So working on the Hardy-Weinberg Equilibrium. We have a vignette and reference manual. So vignette first, again, set up for like a paper, a lot going on here. Really helps overview this and talk about the Hardy-Weinberg Equilibrium. I kind of had to refresh myself a little bit. So that has to do with frequencies of alleles and genotypes in the environment and whether they're in equilibrium, etc. And so really what you're doing is a lot of these tests are testing whether or not your observed allele frequencies, genotype frequencies, match the expected ones under the Hardy-Weinberg equation. So a lot of these, you can do a lot of things like chi-square tests, etc. So this has a lot of good, math and examples. And actually, I'm going to scroll down to 8, which I like. is the start, I'll keep going with 8, of an example session, which I'll replicate in part in the R code part. All right, let's go to the package. There's a lot going on here. I think a lot of them is going to be the sort of the HW, Hardy-Weinberg, and then the different types of, plots, chi-squared, exact, etc. Okay, getting near the end here, we have IRR, various coefficients for iterator reliability and agreement. So there's just the reference manual, which is fun. And there's some data sets here, like anxiety that's used a lot, diagnoses, but then a lot of these just coefficients. So let's see, keep going. Okay, show a few. So like the kappa coefficient of concordance. We got the Flint coefficient of 1- and 2-way models. Here we go, interclass correlation coefficient, ICC. Iota coefficient. Let's get, okay, there we go, Cohen's kappa. Sort of the index of iterator agreement. That's kind of pretty standard. We got another type of kappa, so on and so forth. Light's kappa, Kendo's coefficient for concordance. So these sort of reliability metrics. Finally, we have vacuum, Tukey's vacuum cleaner. These are procedures developed by John Tukey in his paper Future Data Analysis. They're FUN-OP, which is full normal plot, FUN-OR, which is full normal rejection, full normal modification, and then vacuum cleaner. So let's look at the vignette, PDF. Vignette kind of goes through these. And so this is set up in the tidy format. So FUN-OP essentially identifies outliers in a vector. And so it's sort of like a QQ plot, but essentially it takes median values and kind of compares them. And if they're too far out, they're sort of outliers. It's sort of a visualization. Some of these areas are kind of out there, while the green ones are sort of within around the median, and then the other ones are good enough. They're undistinguished. These are the median-esque ones are excluded because that's like where the comparison is coming from. It's spit out a table like this. We'll look more into that when we actually run it. FUN-OR, FUN-ON. So it actually, instead of just, I think, identifying outliers, it identifies them and then rejects or modifies them as needed. So I think the idea here is if you have these different values and some of them are outliers, it cleans it up and modifies them. So whatever that gives you. And then finally, vacuum cleaner is sort of an extension of this FUN-OR, FUN-ON. It takes all these variables and it outputs a set of residuals which can understand the variance and do analysis. So it sort of does stuff, vacuums it up, and cleans it, and then spits out a residual table. And then here's the package. Looks like really there's only the FUN-OP, FUN-OR, FUN-ON, and vacuum cleaner functions, and then one other function here, and then 3 data sets, table 1, 2, and 8 from actually the original paper. Great. We will turn our chipmunky eye to running these examples in R itself, playing around. Here we are in R code days, happy coding days of old. Anyways, you need to load in the various packages. If you haven't already downloaded them and installed them, you need to do that, and then run library. Also, if you have, sometimes I think some of the graphing gets off, so I run dev-off just before, just to make sure the graphs look right. All right, let's start with dhur. So there's 4 different setups, and these are going to be shiny sort of tutorials that'll play. So let's get going with that. Okay, here we are in a shiny app. So this is a tab in our browser, playing around with R. Okay, so there's some places to run code, do stuff like that. Introduction stuff. Some of it's a little hard to read, but and pretty basic. But some of the things I did find here that were kind of useful. Creating data vector. It's pretty basic stuff. This might be a good refresher if you want to remember how to do some basic things like factoring or levels and label. The one useful thing I found in here, especially, was not combined data, but long to wide transformation, and so transfer between long and wide. I normally do that in SAS because I didn't really know how to do an R, but this is a good reference there if I need it. Okay, we're gonna close out of that. That's all we need. Where's R? Okay, we're gonna stop this. Okay, so that was all right. Let's go to Munging. Shoop. Okay, and this is seems to be formatted a little more nicely. So there's skills you want to do. Okay, next topic. Sort of pretty basic stuff on getting to know the data, blah blah blah, knowing about the variable, fancy moves. Now this is where things start to get kind of broken. Where like I see there's supposed to be this picture, but it's not loading. I don't know if that's just my browser or I don't think so. So it's kind of, and again, you kind of get to these 5 guns, but you don't actually know what they are because you can't see in the picture. So it kind of seems a little bit lacking. So there's that. I know these are still under development, so I'm not going to ding it too bad here. Anyways, going back here, and now it turns out that these next 2 don't actually work. I'm going to just run them. They start loading, but then nothing pops up. They get errors. So this tutorial is fairly incomplete. There might be 1 or 2 things you can get out of it, but on the whole, I don't think it's that up to spec here. So with that, then, oh yeah, it's going, but it said it's not working. Yeah, spitting out things. Yep, and not working. Okay, so Kern Lab. So let's take a look at this. I like to use the list function just to see what we got here. Again, we got quite a few things going on. So these are just some examples. They pull out here, and use the spam data, and then create as a matrix, initialize a kernel function. Again, a lot of stuff I don't really understand what's going on here, but it runs, and so if this is useful, if you're wanting to calculate kernel matrices, you see a matrix, this rows and columns being spit out, you can do different expressions. Like I said, sort of mystical to me, but it looks like this seems to run pretty quick and easily. Here's an example using a promoter gene dataset, training set, and run and display a support vector machine, so we're just going to do that for this gene. Okay, here's the support vector class, some information here, and probability model, etc. So it looks like this kind of works, but I can't really gauge how useful it is because I don't quite understand it, but there it is for you. This explanation is supposed to be, look at all these things I'm an expert in. This is like, hey, these things look interesting. It might be useful, whether or not I particularly have expertise in them or not. Anyways, let's finish up by making some cool graphs. Look, oh wow, we just replicated that really quick here using the code they provided. That's pretty cool, this classification plot. And let's see if we can get that sweet spiral plot too. That's pretty cool. All right, and ending on a fun note here with that Kern test. Now we'll go to Asymp Test. Again, let's look at it. And really, there's not very many functions. There's actually more functions than in the PDF. I think some of these might be maybe added so far or just internal. I don't know. Anyways, let's make some random data. We'll make an X and a Y variable. And then let's just run Asymp Test is essentially like a t-test, seeing if the mean of X and Y is different. So it looks pretty simple if you've ever run a t-test in R. Here we go. That's significant. There's a difference in means of negative 1.2. You can also do this D means, which is the difference in means is actually the same as just mean, so I'm not sure why there's this thing. But then there's also ratio means, which I don't really get too bad, but it definitely gives different output because you're doing ratios rather than differences. So ratio, I guess dividing them rather than taking the difference. And then finally we have just a t-test to show you just how similar it is, and this is well just two sample t-test. And if you see the t-value is negative 5.136, and that's actually the same as just these Asymp tests up here. And then you can actually do these Asymp tests with a variance. And so I did a variance here, looking if X's variance is greater than 0, because the alternative is greater, and spits out stuff here. So that's useful if you find it. It's pretty simple stuff, but you might find niche uses for it. All right, on to the Hardy-Weinberg. Yes, ecology and genetics class is coming back to me here. Okay, got a lot going on here. So let's do some basic stuff. We're going to create an X, which is going to be essentially numbers of three different genotypes. So MM, so the heterozygote, MN, and then NN. And we're going to run a test on it, and a chi-square test. And, okay, we got a p-value that's not significant. So what this says is there's no evidence to reject the Hardy-Weinberg equilibrium here. So looks like it is under equilibrium. It's not deviating from it, which would be the alternative. You can do this for more specific things, like, for example, genes on the X chromosome. So this is a new set of alleles run here. And we don't just have the genotypes, like A, 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 B. We also have just the alleles A and B frequencies. And then we can do this with X linked. And at least when you're looking at both X males and females, it is significantly different here. The p-value deviates from the Hardy-Weinberg. So there's not a Hardy-Weinberg equilibrium, this observed frequencies. You can actually do some power analysis here. So I'm going to run this example here with the same sort of allele frequencies we had up at the basic. And then from what I understand, you can set theta to different values, like 4 and 8. How it's set up, it looks like this is replicating the alpha value as close to 0.05, and then this is actual power, achieved power, or observed power, and that's well above 0.8, so that looks like this is enough frequency, enough counts of each of these alleles to accurately test whether or not it was significantly different from the equilibrium. And then you can also do plots. These are some built-in ones. These ternary plots, which I haven't really used, but they're pretty interesting. I think they can help sort of flesh out a lot of information about how the alleles are distributed. So it builds this plot here, A, B, 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 and then it spans it out. It takes a little bit here, so you got to be patient. And I have two different versions. I think changing the region will kind of change these sort of bands that are generated here. So here's one of them. Okay, it's going to keep going. Oh, sorry, that's a QQ plot. Let's go back here. So this is like region 1, setting up those bands in region 7. I don't exactly understand the difference, but all the plots remain the same. So that's kind of interesting if these plots are useful for you. And then here's a QQ plot for observed and expected p-values. So that's pretty cool. That would certainly make your Hardy-Weinberg equationing easier if you have to do this a lot. Turning on to IRR, we will look at it. Okay, got a variety here. So let's just start with raw ingredient. We're going to pull this data video, and I'll print it because it's helpful to show you. So you have these scores with different videos, and here are the different raters. We can see a lot of them are giving them essentially 4s or whatnot. Sometimes they all agree, sometimes they don't quite agree. And so you can just do raw agreement for this video. It looks like of the subject, 20 subjects, 4 raters, about 35% agreed, I think, the whole time. But you can set the threshold differently. So if you set to like 1 here, I think that allows for tolerance of 1, so like 1 difference. So about 90% of the raters agree on like, I think, all but 1 difference. And then here's some other just correlation coefficients, etc. So the interclass correlation coefficient, we'll do data anxiety. I'll show that again. or not again, but show it. So there's 3 raters, looks like 20 samples. We'll do this 2-way and just do agreement. So this calculates the internet correlation. So we have the actual correlation here. We have a p-value. It's not significant, etc. We do kappa just for 2 raters, for example here. 2 raters, we can get a kappa value, a z, and a p-value. So it's not significant. You can do 10 to the concordance. And for all 3, this was significant. And another cool thing about this package is you can actually get sample size calculation if you're going to do these things. So the example they give is testing the null. It's going to be 0.07 versus alternative, which is greater than 7, given that kappa is 0.85 in both raters. Outside 50% the subject is positive. So we can sort of set this all up here of like given what we're trying to experiment on and run this. And it looks like to run this experiment with enough samples to accurately detect a true difference if it does exist, it's 96 patients or observations or whatnot, whatever you're actually observing. Okay, let's suck things up and clean house here with our final package vacuum. We'll view it as we do. Okay, so let's start with fun ops. So first we're going to do this on a short vector. So we have 1, 2, 3, and 11. 11 is clearly an outlier, so let's look what it shows. Okay, so then what it does is like for 2 and 3, these are sort of the median. It excludes those because those are sort of the measurement they're going against. And 1, so it detects whether it's special false, so it means no, it's not that much different from these mean ones. But 11 here, the y value, is true, it is an outlier. If we look at table 1, actually from within the package, you can see here that some looks like the ones that are outliers, there's 2 of them. There's 473, and 454, those are larger than the rest. If we're going to do phenor, so we can do that on table 2, and it'll spit out this table, and then you can actually show which ones our values essentially were dealt with that weren't in table 2, I guess. Anyways, and then you have vacuum cleaner that will clean up and spit out residuals. Did that already do that? So fast? Yeah, okay. So, take that with what you will. Those are the R examples. The moment you've all been waiting for, scoring and classification. We'll start with Dr. Dhur, and I'm afraid I have to give this a 1. It was pretty much incomplete, and this was a shiny tutorial. Kern Lab, which focuses on machine learning, I give it a solid 3. I don't understand most of it, but it seemed well put together. Asymp Test is 2. It's a basic test. It does them fairly well, but there's not a lot else. It's pretty simple, not a lot you can do with it. Then Hardy-Weinberg, I gave a 4. This is a basic test, but for genetics and ecology specifically, so great if you need to mess around with Hardy-Weinberg. IRR, again, our basic test, these are with reliability measurements. Again, I give it a 4, pretty solid set of functions. And then vacuum, give it 2. Seem to be fine. I don't know how, it's pretty basic test or a classic test, really. I'm not sure how, if you'll ever need to use any of these things in real life, but it's good to go back in some of these classical considerations. Finally, let's have a little fun with a short package called Fun. Lighten up these talks here. Boop, boop, boop. Package Fun here. We'll list it up. There's a bunch of different fun little games. I won't look at all of them. Let's look at some of the most interesting. We have a lights out game, which is going to run this. It's going to pop up here. I'm going to move this, you can see. And it's a sort of simple launch game. Anything you hit, if you turn on a light, it turns lights around it on, and you try to essentially get all the lights out. I am not good at this, so we'll clear up with that and move on. Another interactive one is Minesweeper, same sort of thing. You get to click these. Okay, there's a lot there. I'm just going. Oh, boom, I died. Well, that's fun. If you want to play Minesweeper in R, you got it. Now, if you want a sliding puzzle, and you can actually change the matrix, you can make this bigger or smaller, but I'm just going to use the default example. And here we go, and you can try to solve it. Get like 1 over here, and then I guess 2 over here, and 3 over here, etc., and make this pattern. So fun. And then finally, I'm going to show you the Tower Hanai. This is a classical game. You can actually set the number of blocks, from trivially 1. This is automatic. You don't actually play it yourself. It sort of solves it. So you could do up to, I think, as many numbers as you want, but then it's going to take forever. So I just did 4 as a good intermediate example. So it's just going to generate. You see, okay, you try to get the blocks from one side to the other without setting larger blocks on top of them. And there we go. It solved it. And it kind of shows you the moves. And you know what? Just for fun, I'll show you 3 as well. So now you know what you're looking for, and you can see the even quicker run through. Okay, got that? Move, boom, 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 done. All right, fun stuff for a fun package. Well, with that, we've finished another fine episode. Episode 6 will be on cleanup. We'll talk a whole sort of range of different packages on cleaning and managing data. So until next time, stay chipmunky.